Okay, so continuing with what we have for this particular differential equation, and again we have just taking terms from each of the series from y out to y double prime, so you have x squared y double prime plus xy prime plus x squared y, and so multiplying what we have in the second order derivative series terms by x squared, we have in the mix 2c2x squared, 6c3 x cubed, 12c4 x to the fourth, and you have plus x times y prime, so you have like c1x, 2c2x squared, 3c3x cubed, and we have x squared times what we have in y, so you have c naught x squared, c1 x cubed plus c2 x to the fourth, and so on, and we have is equal to 0. Now, out of all the terms throughout the addition, okay, the lowest degree term is going to be c01 times x, and this is the only first degree term that exists. And so if I were to align what I have here with CO1 times x equal to 0, it turns out that CO1 is equal to 0, and there will be a bit of a domino effect that is created where as we go up, say, to odd degrees in x, you're going to have like CO1 x cubed plus terms in x cubed that will have constants with a subscripted value of 3. And what's going to happen is that from C1 equal to 0, you're going to have all the other odd numbered subscripted constants also equal to 0. So you have C of 3, C of 5, C of 7, C of 9, and so on equal to 0. Now as for what we have in the case of even valued subscripted terms, now we have in the mix, okay, for what we have in x squared, we have 2c2x squared plus 2c2x squared, where we have 4c2x squared plus c naught x squared is equal to 0. So we have, in short, we have 4c2 plus c naught is equal to 0. And we have c of 2 is equal to negative c naught divided by 4. And if I have 16c4 plus c2 from the x to the fourth terms, I have c of 4 is equal to negative c2 over 16. And we have in the higher order ranks, and we have in 6th degree, we would have 36. C of 6 plus C of 4 is equal to 0, and we would have that C of 6 is equal to negative C of 4 over 36. Now, placing what I have in terms of C naught, again, C of 2 is equal to negative C naught over 4. C of 4, you would have like negative 1/16 of negative C naught over 4, so that would be C naught over 64. And C of 6, okay, that would translate out to what we have with negative C naught over 2304. And now I'm going to provide a bit of a shortcut, and we have with C of 2, now we have negative C naught over 4, and I'm going to break this up in terms of powers of 2 and powers of factorials. And here we have negative C naught, and we have over 2 squared times 1 squared, and 1 is going to be 1 factorial. So I have C of 2, I have negative C naught over 2 squared times 1 factorial squared. Now for C of 4, okay, I'm going to have C naught over 64, but branching out, I'm going to have 2 to the 4th power, where the power is the same as the subscripted value for the constant, and I'm going to have left over, I'm going to have 2 squared, or 2 times 1 squared. And now for C of 6, I have negative C naught over 2304, and we'll have negative C naught all over 2 to the 6th, which is 64, and taking into 2304, that is going to be equal to 36. And so you have 3 times 2 times 1 raised to the 2nd. So we have for C of 2, we have negative C naught all over 2 squared times the square of the factorial of 1. C of 4, I have C naught all over 2 to the 4th times the quantity of 2 factorial squared. And for C of 6, I'm going to have negative C naught over 2 to the 6th times the square of 3 factorial. And so for what we have here, I have C of n is equal to negative 1 to the n over 2. So whenever n over 2 is odd, we have negative coefficients, and whenever n over 2 is even, the terms or the coefficient is going to be positive. And again, I have what's going to be n over 2 factorial squared, and I have times 2 to the n. So I did a bit of a commutative switch in the denominator. Now if I let n be equal to 2k, just to get rid of the fraction, Okay, so c of n becomes transformed to c of 2k, and I'm going to have negative 1 to the k, c naught, and for n over 2 factorial squared, this will translate out to k factorial quantity squared, and 2 to the n I'm going to have as 2 raised to the 2k. Now going back to what we have for y, again, we had that our r of 1 was equal to 0. And so again, we have y was equal to the summation as n goes from 0 to infinity of c of n times x to the n, and putting n in terms of 2k. Again, so we have in the rewrite, so n becomes k, and we have in the series, we have the summation as k goes from 0 to infinity, and I have a c of 2k times x to the 2k, and filling in, so we have with c of 2k, and I'm going to move the constant c naught out to the front. Now I have negative 1 to the k times x to the 2k, and again I have k factorial squared times 2 to the 2k. And for what we have in the mix as we get closer and closer, and I'm just going to mention, okay, so I have with x to the 2k all over 2 to the 2k, and just condensing. So I have x over 2 raised to the 2k. So that's where this is going to come from. So I got c naught times the summation as k goes from 0 to infinity, negative 1 to the k. And now I have for k factorial squared, I'm going to break this down and I'll show you why. So I got k factorial times k factorial, in this case k plus 0 factorial, and I have times x over 2 raised to the 2k degree. And this will translate as a Bessel function of the first kind of 0 order. Okay, so if you notice, okay, for this particular result, this is of the form where we had the Bessel function of order 0. Okay, and again, I have negative 1 to the k, k factorial, and you have k plus 0, thus the k factorial squared, and you have x over 2 to the 2k plus 0. So for this final result, okay, you have the Bessel function of the first kind of order 0.